Okay, well, let's continue on with this red shirt problem under the ideas that we were spoken of before of a one-tailed test. In this example, right here, the researcher obtained a mean of 16.5% for the 36 males who were served by the waitress in the red shirt. And here's how we compute that Z. The calculated, obtained value of Z will be precisely the same. There's no difference. A Z-score of Z equals 1.75 is in the critical region for the one-tailed test. And by the way, and let me read the rest. This is a very unlikely outcome if the null hypothesis is true. Therefore, we reject the null hypothesis and conclude that the red shirt produces a significant increase in tips from male customers. And here's how we would write it in a research article. Wearing a red shirt produced a significant increase in tips, Z equals 1.75, and P less than 0.05. This is the first time we've seen this. The probability that we obtained this sample mean, given that the null hypothesis is true, is less than 5%. Therefore, we reject the null hypothesis and enjoy the statistical significance. You'll notice also that they specifically said it was a one-tailed test. But here's a graphical depiction of that. The critical value is 1.65. The obtained was 1.75. No decision. Bang, you're done. You don't have to think it through. So we would be rejecting the null hypothesis in that case. Now, one of the things that helped, again, was the 36 participants. That wasn't irrelevant. It made a nice low standard error. So let me try another problem that's one-tailed. And in this case, we have a gigantic sample. It's a little different. Consider the mean number of saccades. These are small eye movements per minute. 1,500, standard deviation of 400. You don't really know this. It appears to be that your eyes move smoothly, when in fact, there are discrete movements, almost like a second hand on a watch. And it may look like it's smooth, but it's actually stopping every 10th of a second, every fifth, or something like that. Your eyes do the same thing. So a sample of 256 people, gigantic sample, takes Sedator, a sedative. Their mean saccades were 1440. Looks like it lowered them. Let's say we hypothesize that Sedator reduces saccades. What are the null and alternate hypotheses for a one-tailed test alpha of 01? I'm going the opposite direction here. I'm again using these subscripts, the saccades among people that take Sedator. I want to start with my alternative or research hypothesis, which would say that it lowers away from the default 1,500. So for the people that take this silly drug, it lowers their number of saccades away from the 1,500. Can I then state the opposite for the null hypothesis? Sure. And what's the opposite of lower than is greater than or equal to? And again, for the sake of completeness, we're including the greater than or equal to. But that's the number of saccades among people that are taking the Sedator. This suggests it doesn't make any difference. It's either greater than or equal to 1,500. It's not going to be a decrease, where the experimental or the alternative hypothesis is predicting a decrease. Now, before we even get there, on what side is the critical value going to be? Isn't it going to be on the left? How do I know that? I'm predicting a decrease, and even if I don't want to go there, I'll just say, hey, look, there's the arrow. Once I can establish this, I can just merely follow the arrow that is predicting to be a decrease. Now, what other sorts of experiments would have a decrease? Weight loss, smoking cessation, in which people are smoking fewer cigarettes, things like that. So what I want to do is establish the critical boundaries on the distribution of sample means. Now, where did this come from? I have my new Z critical. We just established that the critical value of Z is going to be on the left, right? Correct, I should say. It's going to be on the left. And then, therefore, I know the critical value of Z is negative, which is, pretty well established by now. Now, how do I know where I can place 1%? Because the alpha level was 0.01. Okay. Now, again, this is going to require just a little bit of energy, a little bit of commitment, because I've noticed, to my surprise, that this has been an issue for students in the past. Can we convert percentages to 4-digit decimals, or can I just convert 0.01 to 4 digits? Yes. What is that as 4 digits? 0.0100. And here's as close as we can get on the Z tables. As close as I can get on the Z tables to 1% in the tail, or 0.0100, is 0099. That's as close as I can get. So I hope you'll inspect the tables and agree with me that that's as close as we can get with respect to that critical value, and therefore it's 2.33. Now let's go through the rest of the problem. A sample of 256 Setador takers shows a mean saccades of 1440, etc. I'm going to calculate the problem's standard deviation, divide it by the enormous N of 256. 400 over 16 is 25. I hope you'll agree with that. Then I'll plug that 25 into the Z formula. 1440 minus 1500 over 25 is that right? What's 60 over 25? That's right. I'm sorry, I got confused there for a minute. I just paused. I just panicked. It didn't look right. Hold it. I'm going to pull this up on my calculator. Holy cow, Scott. Wow. Yes, 2.4. Holy moly. Senior moment. Everything's fine. So yes, 1440 minus the 1500 over 25 is negative 2.4. Everything's okay. No need to call anybody. So here we go. Negative 2.4. So the math is fine. And sure enough, by an eyelash, look how close it is. The 2.4 exceeds, it's over here in the critical region, right past the negative 2.33. What's my decision? Reject the null hypothesis. I'm going to reject it. It's not really a decision. It's just basically the outcome that was on the scale. So what contributed to that decision was, and what helped the researcher, even though it was just by an eyelash, was that huge N. The N made the standard deviation very large, or the standard error very large, which basically allowed the Z to be even larger. I should say it compensated, if you will, for the large standard deviation. Dividing by that huge N just really made this a favorable outcome, because it actually lowered this 25 even lower than it could have been because of the large standard error. But again, all things equal, not to confuse the issue, is that the larger the sample size, the more likely, all things equal, that you'll enjoy statistical significance. And that sure helped here, because it barely exceeded that negative 2.33. So again, no decision to be made. Here's the goalpost, if you will. Here's just exceeding the goalpost out here on the left. And that is going to be a firm decision of rejecting the null hypothesis. We actually did obtain statistical significance. This one ran really long. I'll try to shorten these videos a little bit.